We're going to start the second half of the webinar now. If you're just joining us, welcome to the Mobilize and Restore webinar series. And thanks to those who have continued on from the research talk. In this portion of the webinar, our speaker, Kevin Thomas, will present some best practices for deep learning models. And we'll take some questions, some more questions at the end of this section, again through the Q&A panel. Feel free to enter your questions during the talk. With that, Kevin, please go ahead.
Thanks, Carmichael. In this second part of the talk, I want to go over strategies for training deep learning models in your own work. But I want to take just one slide to repeat something I said in the first half of the talk, because it's going to frame our whole discussion for part two here. Deep learning is a computational technique used to create neural network models, which are pieces of software. And these neural network models provide a mapping from an input to an output by learning from example data. So you give a deep learning model an input, and again, it gives you back an output. So for example, we might want a model to learn how to take in X-rays as input and produce an assessment of OA severity as output by showing it example images previously labeled with OA severity by a radiologist. Now, when you're training a model and evaluating its performance, the metrics you use to evaluate how well your model is doing depends on what type of task you're trying to automate. So for example, classification is a type of task that deals with sorting things into categories like mild, moderate, severe, or healthy versus sick. And one metric you might use to assess how well your model is at a classification task is the F1 score. Now, a different task is regression, which is the idea of assigning a numerical value to each item, each piece of data, each observation or subject you might have. So this is valuable, for example, if you want to assign disease severity scores to each of your subjects based on data you've collected from them. And a third common task that's automated with deep learning is segmentation, which focuses on finding the important parts of a larger image. So the example I gave before was that you might want to segment the cartilage in your subject's knee MRIs so that you can then measure the health of that cartilage. And you might also want to use domain-specific assessments to measure how well your model is doing. This gives you the chance to use your personal expertise in your domain to identify what the model actually needs to be good at. So this often involves using a model's output to calculate some assessment of patient health, and then assessing how well that health measurement agrees with the gold standard. So for example, in the first half of my talk, I first segmented the cartilage in my knee MRIs using my model. And then I used those segmentations to generate T2 maps to measure cartilage health. And then I compared how well the T2 maps from my model agreed with those of the radiologist. I'll also give you a biomechanics example here. Researchers in my group used a neural network to do markerless motion capture. And then they used this markerless motion capture data to estimate the severity of cerebral palsy in children, and found that they could do it quite well relative to the gold standard of using motion capture and calculating disease severity from that. Now, after you decide what metric you'll use to measure model performance, you then need to figure out which portions of your data you'll use to calculate those metrics. Now, remember from the first half of my talk, I had 40,000 knee X-rays from 4,500 subjects. And this means I had several images from each subject collected longitudinally. And I split this data up so that 80% of the subjects went into my training set, 10% of the subjects went into my validation set, and 10% of my subjects went into the test set. And in deep learning, you'll often iteratively build a model using your training set, check how well it's doing by evaluating it with the validation set, and then go back and adjust your model to try to make it even better and repeat that process. Now, over time, this makes it so that the model's performance on the validation set might be a little bit of an overestimate of how well it will do on new images from new subjects it's never seen before, because you're constantly updating the model to try to get it to work even better on the validation set. And you're tweaking it with the validation set as your focus. So that's why it's important for me to split up my data into 3 pieces here. It is specifically split up at the subject level instead of the image level, so that the model can't cheat and remember what a certain subject's knee looks like, which might happen if a given subject had images both in the training set and the test set. And it's only at the very end, after you've decided that you're completely done tweaking and tuning your model and assessing it on the validation set, you take that version of the model that performs best on your validation set, you freeze it, you lock it in, and you assess how well it does on the test set to get a robust assessment of how well it's going to do on new data it might encounter when it's actually being used. Now, say you do this, you've chosen your validation, your performance metric, and you've split it up into your data set into 3 pieces, and you're in the process of iteratively tweaking and tuning your model. And you're at a point where you assess the performance of your training set to have a value of 0.95. But on your validation set, you notice that your model's only performing at a value of 0.7. And you know from prior experience in your field that human experts tend to have a performance of 0.9. So your training set, your model's doing even better than human experts on your training set, but it's not doing quite as well on your validation set. This tells you that your model is doing something called overfitting, which means it's kind of memorizing the super fine details and even the noise of your training set to the point that it's actually not learning generalizable rules that can allow it to perform well on the held out validation set. So when this happens, there are a number of strategies you can use to improve model performance and to get rid of the deleterious effects of overfitting. And to start out, you might look at a plot like this, where on the x-axis, you have your epoch of training, which is the number of times that your model has seen every single observation in your data set. So for some of the examples I've given, this is every time it's seen the thousands of images in my training set. And that's the x-axis. And the y-axis is your loss, which is kind of the inverse of performance. So over time on the training set, you see the model's getting better and better with this orange curve here to the point where it has a very low loss. But at some point, the model's performance on the validation set starts to level off and then maybe even get a little worse. And it's kind of at this point here where you see the separation between training set loss and validation set loss. It tells you that the overfitting is starting to happen. And so one strategy you can use to address this is called early stopping. This is the idea of saving a copy of your model after every epoch of training, and then stop training when the model's performance starts to get a lot better on the training set relative to the validation set, and then go back and retrieve the last good copy of your model, somewhere probably around here. Now, another strategy for addressing overfitting is to reduce the size of your model. And this relates to maybe applying regularization, which penalizes how many non-zero weights your model's using. It can also involve reducing the number of layers in your network or reducing the number of features per layer. And then a third strategy is data augmentation, which I'll go into a lot more detail here in a minute. So for some of my research, when I wanted to develop a model to automatically assess osteoarthritis, disease severity from X-rays, I had 20,000 left knees and 20,000 right knees in my data set. But these models need a lot of data to perform well. And so if I just took the mirror image of each of those left and right knees, I now have 40,000 left knees and 40,000 right knees. And this was the motivation behind the use of data augmentation. But instead of just doing mirroring, I applied a lot of different transformations so that while I was training the model, each time I was going to show an image to the model, there was a 20% probability that I just took a large square crop out of the middle of my rectangular knee X-ray and fed that directly into the model for training. But the other 80% of the time, instead of taking the large square crop out of the middle, I would randomly shift up or down where I would take that crop from to get the model ready to perform well on images where the knee might be located in an unusual location. And I would also then sometimes take a random additional crop in order to mimic zoomed in X-rays or people with larger or smaller anatomy so that the model would be able to perform well on that too. From there, I would add a random amount of noise to get the model ready for performing well on images from machines that might be a little noisier or blurrier. And then I would randomly flip the model or mirror it with 50% probability and also randomly adjust the contrast in the images. Now, you can see the results here, where in the top left corner, I have the original knee X-ray, and the other images show many different versions or augmented copies of that image that were also used to train my model. And you can see here, it increases the effective diversity of my data set and increases the effective size of my data set, which can boost performance and can also help prevent the model from overfitting. And I think that when it comes to data augmentation, this is an opportunity to use some creativity and to use some domain expertise. One of the things that I was thinking about when I was designing this augmentation scheme is to try to mimic the modes of variation that I see in my own data set. So, I knew there were right knees and left knees. So I'm going to do some of these random operations to make the right knees look like left knees and make the left knees look like right knees. And I also saw in my data that some of the images were just darker than others. So that's why I added this random contrast augmentation transform. I think that researchers in the field of biomechanics and medical imaging are really familiar with the data sets that they're working with. And this gives them the opportunity to apply really interesting, valuable data augmentation strategies. So I want to give one more example from the field of biomechanics. And again, I'm going to go back to the idea of pose estimation key points. So there's been a lot of research recently that looks at taking standard video footage of a person, applying a key point detection algorithm to find all the major joints of the body. And then that gives you time series that describe how the patient is moving in a video. You can feed that information into a neural network to generate some kind of report, some kind of assessment of their health or human performance. And so when you do this, some of the augmentation strategies that you could potentially use for key point detection algorithms are to maybe add noise to those key point locations to simulate imperfect key points. Another idea is to randomly remove a key point to simulate undetected key points. And one other idea could be to shrink or stretch the distance between key points to simulate subjects that are closer to the camera or moving closer or further away from the camera throughout the course of a video. And I think that this is one area where it's kind of fun and challenging to come up with an augmentation scheme that could potentially boost the performance of your model. So in conclusion, one of the first steps you want to do is to identify what type of model you're going to build, what you want it to do, and how you're going to measure its performance. Then we talked about splitting up our data into training, validation, and test sets to evaluate our model in an unbiased fashion. And then we talked about watching out for overfitting and trying to adjust our strategy for model development when it starts to arise. So with that, I'll pause again and answer any questions you might have.
Great, thank you, Kevin, for another great talk. So we'll go and switch back to questions. So go ahead and get them into the Q&A panel whenever you're ready. I'll start off with maybe a couple here. while we wait on them to come in. The data augmentation part is really interesting way to expand your data set when you really do need a ton of data. You talked about a lot of the ones that worked, and I really appreciated you talking about looking at your own domain expertise to figure out what those transformations should be. Were there any transformations that you tried that you were surprised didn't work?
Yeah, so it was kind of interesting. You can take the approach of doing this like a very systematic kind of leave one out approach to assessing how well the transformations are. And we didn't necessarily do that for our research, but there are findings in past research that show that there are certain deleterious effects that you could potentially have if you augment in a way that forces your model to learn something that might not be really relevant to your actual task. So we didn't necessarily identify anything like that in our own research, but we did find that when you're changing a model during the training process, you need to be very careful about also processing an image in a similar way at test time, for example, while you're using it during in practice. So one example of that is if one of your transforms is processing all of your pixels so that they're between the value of 0 and 1, then it's very important that during test time, you also process all new images so that the pixel values are between 0 and 1. And you need to do that processing in the exact same way you did it in training, because that's how the model learned to generate its predictions. And if you change the distribution of the data, it's going to start to have problems.
Cool. So a question from John Davis: how useful is transfer learning? For example, if I had a small data set of foot X-rays and wanted to diagnose ankle arthritis, would it be a good idea to start from a model pre-trained on knee or chest X-ray data? Is the same true for very different tasks, like pre-training on ImageNet for the same foot X-ray task?
Yeah, that is extremely interesting. And that's been an area where I've done some work in the past. I was really interested in investigating whether you could train a model on a few different X-ray types from, say, 3 different anatomies, and then try to fine tune on a 4th anatomy and see how well that does. And in my own experience, I was pretty surprised by how well ImageNet pre-training does. I think there's a lot of work in prior literature that shows that if you have one knee X-ray data set and you pre-train on knee X-rays and then you fine tune on more knee X-rays, there's good evidence in the literature to suggest that that type of pre-training will boost performance, because you're pre-training on the very similar task to what you're fine tuning on. But when it came to pre-training on chest X-rays and fine tuning on knee X-rays, for example, in my own work, I actually found that that was not as effective as pre-training on ImageNet. And I think part of the reason for that is that ImageNet just has an incredible diversity of images. There's 1,000 different classes and 1,000 images per class. So those ImageNet models have the opportunity to learn really rich feature representations that are a great starting point for any visual task. And pre-training only on chest X-rays potentially might not be as effective, because a chest just doesn't look like a knee, and you're only giving your model the opportunity to learn those chest relevant features during the pre-training process. But that's a great question, and that's something that I was also very interested in the past.
Cool. So maybe another question. So you talked a little bit about train validation test sets, and it's very important to have a validation set. Maybe 2 sub-questions there is, I think some people don't have a validation set. What are they giving up from that? Or are there applications in which maybe you don't need a validation set? And a second question could be, I think in other parts of machine learning, not necessarily in deep learning, cross-validation is used often, but it's used a little less in deep learning. I didn't know if you had any thoughts on that too.
Yeah. So I would say, in general, it's usually good practice to have both that validation set and that test set. And the reason is that you just don't know if you're, during your training process, if your model's overfitting or if it's underfitting, or you don't know whether you should continue to work and refine your model before it's used in practice if you don't have that validation set. And it just gives you this unbiased assessment of model performance before you deploy it or before you check it on the test set, and also gives other users confidence that you've assessed it in the right way. But you bring up an important point with cross-validation. I think one reason why people might be hesitant to use a validation set is that they might have relatively little data and they want to use it all for training if they can, because they don't have very much of it. And I think cross-validation is one valuable strategy for reducing the size of your validation set and getting as much as possible with the limited amount of data you can use. So the idea of cross-validation is that, instead of separating all of your training and validation data into 2 chunks, you might separate it into 5 or 10 different chunks, train on, say, 9/10 of the data and do a validation on 1/10, and then iteratively do that 10 times before you evaluate it still on a held out test set. One reason why it's a little less common in deep learning is that these models are pretty computationally expensive to develop and train. So training 10 different copies of the model can just take a long time. So it's a little bit more common with other areas of machine learning where the model sizes are a little smaller and the models are faster and easier to train. But it's something you could still do with deep learning too.
Awesome, thanks. So I'm not seeing any other questions. So I think with that, we'll go ahead and wrap up. Thank you again, Kevin, for a great talk. And thank you to everyone for all the great questions. Please be sure to click on the link that will appear at the conclusion of the webinar and take our survey. That'll really help us improve the webinar series and choose upcoming topics. This webinar series is supported by 2 grants from the NIH, including the grants that support our Mobilize Center and Restore Center. We're grateful for the support which allows us to run these webinars and other events. Thank you everyone for participating. We hope you'll continue to stay involved with our centers, and that we'll see you at a future webinar. Bye everyone.